200 to Chapter 8. This is the last chapter before the next exam. So I've got a few things to go over in this chapter, and then you'll be all set for Exam 3. A couple of reminders, homework is out there. That's due the 29th. Please see me during office hours if you've got questions over getting ready for the exam, or if you have questions over Quiz 3 Exam 2 grades. We can talk about those on Zoom as well. If you're considering withdrawing, that date is May 8th. And again, I'm happy to talk with you if you have any questions about that process. So what's coming up is Exam 3, April 29th, and the solubility rules is a part of that exam. So I've emailed you this Serious Solids app. It's a great way to practice these solubility rules. So for the week of April 27th, Chapter 8, Exam 3. So if you take a look here, this is Chapter 8. This is aqueous reactions, and it's an introduction. Well, you have very likely already covered these in Chem 152. Okay, so we'll go and cover those again. Not much has changed. We might go in a little bit more detail on the precipitation reactions than what you've seen, but this content is very similar. Acids and bases we will talk about briefly, and titrations, that's part of the labs in 200L. But those are really covered in Chem 201. Same with oxidation reduction reactions. That's why this is an introduction. These will definitely be covered in 201, Chem 201, if you take that course. And gas evolution reactions, what I cover in this class is very similar to Chem 152. So let's get started. As I said, this is an introduction to solutions and definitely aqueous. So that's a real key that we're looking at here. So it's really important in this chapter to be clear on what these definitions mean, because sometimes we hear words and we think right away, well, a solution is a liquid. That's not the definition of a solution. We want to be really clear what defines these things. Okay, so a solution is a homogeneous mixture. The air you're breathing right now is a homogeneous mixture. It is a solution of gases. Typically we think about a solution being liquid, but it doesn't have to be. The solvent is the major component, the solute is the minor component, and what I already said was this chapter, aqueous, that's where water is the solvent. So that is the majority of the chemistry you will study is until you get to organic chemistry, and then you have a lot of different solvents. So these are our working definitions for this chapter. You can also have broad terms, very general terms like dilute. That was a very dilute solution, or wow, that was really concentrated, that was really strong. These are some terms maybe you've heard before. That's talking about how many particles are in there. Okay, so that's a concentrated, this is a dilute. That's very general. Well, of course, we're going to be quantitative in here, so we have quantitative definitions as well. So molarity will be the most common one that we use, and that's moles of solute over liters of solution. So right away, when you see capital M, you should rewrite it as moles of whatever the solute is and liters of the solution. So that's molarity. If you have lab at Miramar, you also talked about molality, mass percent, but this is the most common one because, of course, if we have moles, that takes us back into the roadmap that we know, grams, moles, particles. So this is where molarity will be used consistently in this chapter. So if you prepare a solution of a specific concentration, and when we're talking about concentration, we're being very specific now, molarity, you calculate how many moles you need. So in this case, they wanted a 1 molar solution of sodium chloride, so that's 58.44 grams of sodium chloride. And look here, they've added the solvent, so they added enough water for it to dissolve. Okay, then you want to swirl it. You want to make sure there's no solid particles. Then you have it reach the mark. Okay, so once it's at that mark, then that is a 1 molar solution sodium chloride. So how do we do this? You calculate how many moles you want. You look at the glassware you have and put that in liters, and then you can calculate what molar of a solution you have. So you can work on one of those now. This is molarity, and this is 22.5 grams of sucrose. And look at the units. The units are in milliliters, so calculate the molarity. So again, right away, I encourage you, capital M, that's moles of solute, liters of solution. So that tells us we need to convert 22.5 grams to moles. There's the formula, so you can get the molar mass, and you need to convert milliliters to liters. That goes there. Those go up here, and you find that it's a 1.85 molar solution. Here's another one. How many grams? So now this case, it's not asking for the molarity. You're given the molarity. So the molarity is a conversion factor, and you're given a volume. So molarity, volume. Many of you may write this as an equation. Again, there's nothing wrong with this. Molarity equals moles over a liter. That's fine. And you can put in your volume, liters, change that to liters, put in your molarity, and then solve for moles. What I want you to also see and be comfortable with is that molarity is a conversion factor. So you could put this in dimensional analysis. So 556 mils, dimensional analysis, then that's mils to liters. And then our molarity, remember, rewrite molarity, 2.70 moles per liter. So if we stopped there, that would take us to moles. We need to go to grams, so then you just do one other step, multiply by the molar mass. And you can see here, molarity times volume gives you moles, times the molar mass gives you 204 grams. So this is a little calculations with molarity. Another place you've seen this is in dilutions. Okay, so right away, dilutions, you should be thinking C1 V1 equals C2 V2. And if you're in molarity, then this concentration, C, becomes M1 V1 M2 V2. Okay, I really want to emphasize what's going on here. If you have a molarity, moles per liter, and you're multiplying it by liters, you have moles. So what you're saying when you say M1 V1 equals M2 V2 is that the moles of the solute equal the moles of the solute, which makes sense because remember, a dilution is adding more solvent, so the solute isn't changing. Okay, it goes from dark yellow to light yellow, not because the solute changes, but because you're adding more solvent. So this is dilution equation, and the concept behind it, the moles are constant. Okay, so how would you prepare a 200 ml solution of 0.25 sodium chloride? And it's from a 2 molar sodium chloride solution. So right away, recognizing that sodium chloride, so this is a dilution. You're going from a high concentration, 2.0, to a 0.25. So if you know the dilution equation, then the main thing is just figuring out where does this volume go. Does that go with the 0.25 or the 2? Keep that straight, and then you can solve for the volume, in this case 25 mils. However, I really want you to be clear on this. This is the how, okay? Not just what are the numbers, but what does this mean, okay? So if you solve calculation, you get 25 mils, great. What that means is you need to take 25 mils of the concentrated solution, that's the 2 molar, and then you add the solvent and dilute it up to 200 mils. That would make a 0.25 molar solution, and you have 200 mils of it. So we've been working with molarity, dilution, or moles over liter, and that, again, as I said, takes you right back into moles. Well, Then you can convert to moles of something else, and you can use molarity again and get to volume of something else. So we're back to stoichiometry, grams, moles, particles, grams, moles, particles. So molarity is the new piece. Everything else should be the same. So here, if we're given a 32 grams of zinc, our roadmap right away should be thinking, well, grams of zinc needs to go to moles of zinc. We can go from moles of zinc to moles of HCl through a balanced chemical equation. And then if we have the molarity of HCl, then we can get the volume of HCl. Let's go ahead and try that. First, got to have a balanced chemical equation. So zinc, hydrochloric acid, and you see the balance here. And then, just as we said, we go molar mass. That gets us to moles of zinc. Mole ratio gets us to moles of HCl. And then the molarity is inverted. So you're dividing by the molarity to get to volume, and you can convert that to milliliters. So the key here is this is a molarity. We're looking for a volume, but that's not a MV equation, okay? That's not a dilution. This is a chemical reaction that is stoichiometry. So I'll emphasize that because if you take a look here, there's volume, there's molarity, and there's a volume, and then it says, what about the molarity? Okay, well, wait a minute, I know that, MV. This is not an MV. This is not a dilution, because look, this is a chemical reaction, HCl, barium hydroxide. Okay, so if we take a look, we need a balanced chemical equation, and you see it's not a one-to-one stoichiometry. So if we just did M1, V1, M2, V2, we would get this problem wrong. Okay, so what we need to do is convert using molarity to moles, and then this is the big piece here. You're converting moles of HCl to moles of barium hydroxide. The MV equation does not account for that. So then you got the volume, and that gets you your molarity of barium hydroxide. So those are some the quantitative questions in the beginning. So we had stoichiometry with molarity, we had dilution, and then we had how would you make a solution of a known molarity. Those are the calculations so far. So what we're getting into next is a little bit of concepts. What happens in solution when we have aqueous reactions? Okay, if we have aqueous solutions. So in this case, there's going to be two fundamental questions that are going to be asked, and that's, is something dissolving? Okay, so does it go in solution? And if it does go in solution, what is then in solution? Okay, so the first question, does it dissolve? If it dissolves, that means that there's solute-solvent interactions. Okay, because those have got to overcome the solute-solute. If it dissolves, this wins out. Solute-solvent, solution forms. If solute-solute wins out, it's a precipitate, only solid forms, it does not dissolve. So this has gone over in more detail in CHEM200 with the quantitative, doing calculations to determine will it dissolve or not. Here we're just looking conceptual, what's happening. And this was talked about in a previous lab activity, but why aqueous is so unique is because water is polar. So we've got partial negatives on water that are attracted to the cations. We've got the partial positives on water that are attracted to the anions. So that is increasing the solvent-solute interaction. Because you can imagine that full positive, full negative, that's a strong solute-solute interaction. But for most ionic compounds, this solvent-solute wins out. And you can see here, this is slowly being dissolved. And the reasons, because the cation is surrounded by water molecules with the partial negatives going in. The anion is being surrounded by water molecules with the partial hydrogens attracted there. So that's the dissolving process, okay? And that's for an ionic compound. So cations, anions. Well, we know other things dissolve. Sugar, that dissolves. I love my lemonade or sweet tea. That's sugar in there. So it dissolves, but look, it's a polar substance, so it's not charged. That's surrounded by the partial charges of water as well. Here, remember, ionic, full ions, full charges being surrounded. Okay, so these are different. So first question, does it dissolve? Sugar, yes, it dissolves. Ionic compound, yes, it dissolves in most cases. Then we say, what's in solution? Okay, so the terminology here, maybe you've seen this before, is an electrolyte or a non-electrolyte. So you put salt in, goes into ions, ions conduct electricity, conducts, the light bulb goes on. Ah, the light is on because there are ions in here. Sugar, remember, sugar is dissolving. We know it's in solution, but it dissolves as whole molecules. It does not turn into ions, so there is no light on. Nothing is being conducted. So this is a non-electrolyte because it's non-conductive. So conceptually then we need to think about what kind of compounds conduct electricity. If an ionic compound dissolves, that will conduct electricity. So for sure this conducts electricity. Sucrose we just showed. If you look, those are all non-metals. It's a polar compound, but it's not an ionic compound, so that's not going to conduct, so get rid of that answer. Same thing here. This is a little misleading because it looks like a hydroxide, but it's actually an alcohol for an organic compound, so it's also a polar compound, not ionic, so that's our silver nitrate. And you can see here the pictures, non-electrolyte we talked about, that's sucrose, strong electrolyte, sodium chloride, and then this actually is one in between, a weak electrolyte, okay? So over here we have a lot of ions, so there's a lot of ions in solution. Here we have no ions in solution. Here we just have a few ions in solution. Okay, that's a weak electrolyte. So we'll just go over those terms here. Strong electrolyte, when it dissolves, it completely ionizes. That's 100%. Okay, everything goes in as ions. Ionic compounds, so we just said sodium chloride. So those are called salts or ionic compounds. Strong acids. You go in great detail in CHEM200 about what strong acids are, but here, in this case, hydrochloric acid is an example of a strong acid, so it ionizes 100% when it goes into solution. Same with strong bases, so strong bases, that would be sodium hydroxide. So now this is a hydroxide group, not an alcohol group like we saw earlier. That's also a strong electrolyte. So weak electrolytes are a little bit different. Still has acids, still has bases on this, but it's an acid like HF, which does not ionize completely. This is an equilibrium or double arrow. We'll talk about that just a little bit in this class. You saw it maybe in Chem 152, but it's talked about heavily in Chem 201. So remember earlier I said strong electrolytes go 100%. Well, really, weak electrolytes, it depends on the weak electrolyte, but it goes like 5%. So there's 5% ions, and there's 95% molecules. Okay, so that's a weak acid, a weak electrolyte. Same thing with bases. They have a double arrow, similar to this percent. So another example of a weak electrolyte and a weak acid is acetic acid. So this acetate is one of your polyatomic ions. Put an H in front of it, it's acetic acid. This is mostly molecules, very few ions going on here. And then lastly, like sucrose, substances that dissolve in water but don't produce any ions. So here's our sucrose. They're dissolved. That's sweet, tastes so good, but they're not ions. Okay, they're molecules fully dissolving, and we know that they're there because of the taste, but it's not conducting electricity, so there's no ions in solution. All right, so now we're going to go to that first question, will it dissolve or not? Okay, So this is a question about solubility. And if you had Chem 152 at Miramar, there are some good labs showing you precipitation, solubility rules, things like that. So we'll talk about some of those and introduce those here. So first, terms. Again, we want to be really clear on definitions. Soluble means that it dissolves in water. And remember, this is aqueous reactions. So if it's an ion, it's going to be aqueous. It's going to be in solution, or a compound you put aqueous. If it's insoluble, it forms a precipitate. So that term, the precipitate, the supernatant is aqueous. The precipitate is the solid. So that's the S in the reaction. So I've posted the rules on Canvas, solubility rules, how I would learn them. In order, it's the same rules. It's a little simplified from the text, but it's the same rules. Put them in order. Here's what your text shows. Okay, so the alkali and ammonium, those dissolve. If they're with any compound, with any anion, they're going to dissolve. Nitrate and acetate, they're going to dissolve. Okay, so these are, it's hard to see on that blue there, but these are the ions that are soluble. Chloride, bromide, iodide are soluble, except with silver, mercury, lead. Okay, so of course CHEM200, those are exceptions. Sulfate soluble, except with this group. Okay, so that's really important to think about, is if you have a soluble rule, then the exception to a soluble rule is that it's a solid. That's what all of these exceptions are. These are precipitates. Okay, so if we go down here, this is the insoluble rules. So hydroxides and sulfide are insoluble typically. Well, we already saw, this is why the handout I have, I think, helps a little bit better with this. We already saw this rule. These are soluble. That's right up here. Okay, so the handout that I provide, it goes in order. So you go from top to bottom. If top rule applies, you take that rule and then you move on. Here's an exception, sulfide, and these are now an exception to an insoluble rule. So if it's an exception to an insoluble rule, that makes it aqueous. Carbonates, phosphates are insoluble, except we just saw already our alkali metals and ammonium. Okay, so let's apply these rules. So I encourage you, whether it's this figure from the book, from the handout, have these as you're working on these problems. I also sent you an app that helps with this. Great practice for solubility rules. Try that out. Okay, so I want you to look at these and go through and just identify, is it going to be soluble or insoluble in water? All right, so hydroxides are insoluble. However, first rule, potassiums are soluble. Silver bromide, if you look, bromides are supposed to be soluble, but the rule before that is silver is insoluble with them, so silver bromide. Calcium chloride soluble, our nitrate rule says it's soluble, even though later lead says it's insoluble. And then the lead sulfate, sulfates are typically soluble. Wait a minute, that's a soluble rule. If it's an exception to a soluble rule, it is insoluble. So this is the starting point, is knowing the rules, and then you can predict products. And that's where we're going with this, is predicting products. So that means we're talking about precipitation reactions. If you have two solutions mixed, then you can think about who's going to react with who. Okay, so if we look here, this is a double displacement, double replacement, and the A then goes with D, and the C is the cation, so the C goes before the B. And the question is, do any of these form a solid? Okay, that's the solubility rules. If a solid forms, then a reaction happens. If they're both aqueous, nothing happens, no reaction. So let's take a look here. This is it's really small up here, but Ki is aqueous, so that means it's soluble. Lead nitrate is aqueous, so of course that's soluble. You put those two together and you think about your options. Okay, so the cations are potassium and lead. The anions are the iodide and the nitrate. Okay, so how you do this then is K and I started together, so they can't be together. K and lead aren't going to be together. Those are two cations, so this is our crisscross. And then now it's new rules, okay? Potassium rules says it's soluble, so whatever it combines with is going to be soluble. That's the same as nitrate. That nitrate rule says soluble. So what's happening then is lead iodide forms a solid. Okay, the rule is lead forms precipitate. So then we have to know that's lead 2. We need to know that lead 2 is the solid and write the correct formula, PbI2, solid. And there's the chemistry. Lead combines with iodide and forms this impressive solid here, and it precipitates out of solution. Okay, let's go for another example. Ki, sodium chloride this time. So then we switch cations, that's sodium and iodide, potassium and chloride. All of those fall into the soluble rule, so there's no reaction. So let's got to be able to write the formulas and predict, will a solid form? So if you take a look at these, go for it. Predict the products. So does that mean a reaction happens or not? And then balance them. See here, we crisscross, and again, silver is an exception. Silver chloride will form a solid. Potassium nitrate does not. Here we're going sodium and chloride and calcium and sulfide. And sulfide rules, sulfides are insoluble. However, calcium sulfide's an exception. It is soluble. That means no reaction. Both solubles, no reaction. Lead sulfate, ammonium acetate. Ammonium and acetate are both soluble. Lead is insoluble when it combines with sulfate, so that's why we have a solid here. So this is the very first part, and then this next part is what I think is one of the most difficult parts in Chem 152. So if you practiced it, if you did it in Chem 152, maybe it's still there, maybe you need to brush up on it, but it's how we represent these reactions. Okay, so we just talked about balancing and writing molecular equations. Then we're going to go to complete ionic. So that's every ion in the reaction we're going to write out with its charge and how many are there. And then there's going to be a net ionic equation, which just means what is happening. What is the chemistry that's actually involved. So molecular complete neutral formulas, complete ionic, as I just mentioned, it shows everything, cations, anions, precipitates, everything present in solution. You need to show that, and then the net, just what's changing, just where the chemistry's at. All right, so if you take a look here, we've got potassium sulfate and silver nitrate. So you need to think right away. First, this is silver sulfate and potassium nitrate, which is going to be the solid. So that's a rules that we need to look at and know. And in this case, it's going to be the silver sulfate. Then we need to balance a chemical equation. Okay, so if we go here, we see that's potassium sulfate, silver nitrate. So our solid is going to be Ag, and sulfate has a -2 charge. That's our solid. And then if we have silver sulfate, our leftover is potassium nitrate. And that's in solution. So this is the molecular that we're balancing, making sure we've got a nice balanced chemical equation. You can see here we've got 2 potassiums, and we've only got 1 potassium here, so let's put a 2 here. We got 2 silver, 2 nitrate, so we put a 2 here. Okay, so now we're balanced with our molecular equation. Well, that takes us to the next one, the complete or total ion equation. Okay, so everything in solution. So what we need to do is go from this compound in solution and see that that's made up of 2 potassiums. Sulfate stays together, SO4 2-. There's 2 silvers, 2 nitrates. So you see how we're taking that coefficient and spreading it to both of those cation and anion. And then if you look, we see that the solid stays together. We don't break that up. And then again, the coefficient gets spread, 2 potassiums, 2 nitrates. So now that's the total or complete ionic. So now you can cross out all the spectator ions, or the ions that aren't doing anything. So if you take a look, 2 nitrate on the left, 2 nitrate on the right, 2 potassiums on the right, 2 potassiums on the left of the arrow. So I'm saying and canceling what's on the arrow. So then we just look at what's left. It's the silver, and the silver is combining with the sulfate, and that forms the product. So that's your net ionic equation. Okay, that's the chemistry. That's what's really happening in solution. These things are reacting. So again, this one, similar. This is strontium chloride and lithium phosphate. So you need to think about what's the solid. So I would write that out first. And this would be the strontium phosphate. And that's your solid. And you look over your leftovers. So if that's strontium and phosphate, that leaves us with lithium chloride. And there's some actually that both precipitate out, but usually it's just one or nothing. So now we've got lithium chloride. So if you take a look here, then we've got 2 phosphates. So I can go back here and put 2 phosphates. And we had 3 strontiums. 3 strontiums, so that gives us 6 chlorines, 6 lithiums. So we need 6 lithium chlorides here. Okay, so we've got that balanced. And now we can go to the complete ionic. This is not easy. Now we're changing things up here. So start with, what are the ions? Okay, so this is chloride, Cl-, and this is strontium, Sr2+. So we go there, then we can say that's 3 Sr2+. And I know there's a subscript and a coefficient, so we have to multiply those. That's 6 chlorides. Same thing here, 6 lithiums and 2 phosphates. So this math is where a lot of trouble happens. What are the charges? 3-, 2+, whatever it is. And how many do you have? Is it 6? Is it 2? You see the solid again stays together. And then we're left with the chloride and the lithium. So that takes us to the net ionic equation. And that's the strontium plus the phosphate equals the strontium phosphate. That's the chemistry. That's what's happening here. So there's a lot of work in this section on precipitation. So I really encourage you look at the homework, practice, come to office hours. But I think this is a lot of tough chemistry to get to these few examples that we've run through quite quickly. The next section is on acids and bases. So this is, again, a major topic of Chem 201. I think it's great chemistry, really interesting. We just cover a very little bit here, okay? So you actually probably covered more in Chem 152 than what we'll cover here in Chem 200 about acids and bases. So you may recall properties of acids and bases, things that you know about acids and bases. Some of the common ones are litmus paper. Blue litmus paper turns red. Acids taste sour. Acids react, gives us this hydrogen gas that we like to light and react. And then there's neutralization reactions that form water and salts. Bases turn red litmus paper blue. So you've used this in lab if you've been in Miramar labs. Bases are bitter, they feel very slippery, so if you clean your oven with oven cleaner, it's It's probably sodium hydroxide. It feels very slippery to the touch. And then these also undergo these neutralization reactions. So we actually saved naming acids for this chapter. We named a bunch of compounds, but we didn't name acids. But good reminder is you probably have seen these or been working with these, okay? So binary means 2 atoms. So think about the ones that you know, okay? So right away, I'm looking at HCl. And then oxyacids, they contain oxygen. So there's some other common ones maybe you've seen with several oxygen atoms. Okay, so these are the acids. H's are present there in the beginning to show you this is going to ionize, and the key with acids, they are giving off H pluses. That is one of the definitions of what an acid is. So I'll start with the ones that you know. HCl, how would you name this? Okay, you've used this, you've named this. This is hydrochloric acid. So the terminology or the systematic naming is hydro, use the element name, chlorine, then add the ic, so hydrochloric acid. Okay, so if you've got that down, you can name these binaries. Okay, remember, 2 elements here, and sometimes we add more to this little naming system. So HCl, hydrochloric, HBr, hydrobromic, and you can continue on and on. This one was seen in CHEM200L lab. This is hydrosulfuric. That's different than sulfuric. This is hydrosulfuric, and this is hydrofluoric, and then you can see here even more than 2 elements, we still do the same, hydrocyanic. Okay, so that's our binary acid. Then we can take a look at our oxyacids, and I want to really emphasize these come from the polyatomic ions. Okay, so nitrate is the polyatomic ion, NO3 minus. And remember, acids have H pluses, so for that to become neutral, we put the H plus with an NO3, and that is the neutral acid. So nitrate becomes nitric acid. So this is nitric acid because it's a polyatomic ion 8, so it goes to ic acid. Then you knew the group nitrite. So in this case, nitrite comes new naming system, nitrous acid. So that's the formula 1H because it needed to make it neutral. That's the acid HNO2. So we got a whole group of these to practice. So I encourage you to pause and work through these. You got to think of the polyatomic ion first, and then go to the rule. Is it 8 or is it 8? Let's go ahead and go for it. So if you take a look here, these are the ones that we've done. The nitrate, the nitrite, so that's nitric acid, nitrous acid. Same kind of pattern here. This is SO4 2-, that's sulfate, that's sulfite, so that should be sulfuric acid, sulfurous acid. This is acetate, we saw that earlier. Well, if it's an 8, we know that goes to ic acid, acetic acid, and these are 8s. Phosphate, perchlorate, so that's phosphoric acid, perchloric acid, and then look at the rules. We said perchloric acid because it was perchlorate. This is chlorate, and we just continue down. Now this is chlorite, chlorus, and that's hypochlorite, so that's hypochlorous acid. So when we know the acids, we know the H pluses that go on with the polyatomic ions. That'll help us get to an understanding of these acid-base reactions. Okay, so acid and base react to form water and a salt. This salt, remember, is just an ionic compound. It could be sodium chloride, it could be any other kind of compound. It's just an ionic. That's a general term for ionic compounds or salts. So it's neutralization because we get to water. And actually the salts, are usually neutral, but if you take CHEM200, you can have acidic salts, you can have basic salts, but here neutralizing it in general, we talk about neutral salts and water being the products. So we saw a nice reaction earlier. Well, look at this. HCl, aqueous, NaOH, aqueous, colorless, colorless. You put them together and you get water and a salt and you see nothing. There's no color change. There's no precipitate. So we have to monitor the pH, or we have to monitor the acidity in order to see a change, okay? And this can be done with an indicator, with a pH meter. So there's a variety of ways this can be done, but you're not going to see a solid, okay? You won't see a color change from the acid or the base. We can add indicators to it, but you're not seeing it from the acid and the base. So titration, typically what you're looking at is you have a known concentration and you're trying to determine the unknown concentration. So this is in the CHEM200L lab, experiment 6, experiment 7. So this is a really important part of the lab, is how do you determine the unknown concentration. So the equivalence point is when your moles of hydroxide equal your moles of H+. So this is the acid, this is the base. When they're equivalent, that's when you're going to have this change. And in our cases, we'll talk about indicators. When the indicator changes, that's the equivalence point. So the indicator gives you nice, distinct color changes when this point has been reached. So that's what we choose, the correct indicator. You do the titration and you get the change, and that tells you when the moles are equal to each other. So what this looks like in a lab conceptually is you start with one of them in the Erlenmeyer flask. So in this case, the acid's in the Erlenmeyer flask, the base is in the burette, and you're slowly adding, so a reaction is happening. Okay, H plus OH is water. You can even see some of the indicator changing there, that something's happening. And then when it gets to the equivalence point, so when you see all the waters have changed, so H pluses, OHs equal all waters, then that's where you've reached your color change and your equivalence point. So practically, if you were doing this, it would look more like this. You'd have colorless, you'd add indicator, it'd still be colorless, you don't see anything. And then when you're adding, you're swirling, you're getting some color there present. And then you go for one drop. You get one drop to want to change this completely. Okay, so what I mean by that is you add, maybe 5 mils, 10 mils, and you're adding large increments, maybe half a mil, quarter mil. And then it's coming because it's starting to get all this pink. And you want one last drop to turn everything pink. That's what you are going for. That gets you to the equivalence point. So what does this mean then? Well, if you've got a volume of what you titrated, you've got a volume of what you started with, and a concentration, molarity, then you should be able to calculate the molarity of HCl. So go for that. See if you can calculate the molarity of the HCl. So if you take a look here, this is solution stoichiometry. It's just now called acid and base, but it's the same work that you've been looking at. So if it's moles per liter times volume, that gets you your moles. Okay, so then if you've got moles, you need the mole-mole ratio. That gets you moles of HCl. Moles of HCl divided by volume gives you your molarity. So of course the volume has to be in liters like here. So this is the piece that's added. It's just now an acid and a base, but it's still molarity, it's still volume, and you can solve for your unknown. So we've got two other sections left in this chapter, and this one's very brief, gas evolution reactions. Okay, so what I want to emphasize is that a gas evolution reaction, okay, the key word there is not a gas reaction, but it's what's coming out. You take two aqueous and then you have this gas evolve out of these two aqueous reactions. Okay, So that's bubbling out, it's coming out. It's the most confusing part is students will just look and say, well, there's a gas for the product. That must be gas evolution. No, it's got to come from two aqueous solutions. So this happens. Acid-base reactions can do this, but we've also seen this before in lab, this gas that evolves. So hydrochloric acid, potassium sulfide, that gives our hydrosulfuric acid, this hydrogen sulfide gas. Okay, so that's H2S gas. This is CO2, SO2, and ammonia. So you can see these gases are here in the products, but remember that's not our only definition. The gases are in the products. The other piece is it comes from two aqueous reactants. That's the piece I want you to see for gas evolution. So all of those are the same. Aqueous, aqueous, then we get a gas. Okay, this one for sure you can see, right? That's bubbles. That's a gas evolution reaction. Aqueous, aqueous, and then a gas forms. You see that happening. In Chem 152, you tested it out. You said, was the gas hydrogen? Did it pop? Is it carbon dioxide? Does the flame go out? So you can test the gases, but the main thing is you can see this for sure, unlike our acid and base where we have to add an indicator. So the key then, recognizing we've got two aqueous, and if we're predicting products of gases, you're looking for what gases would come out of this. Okay, so if we take a look here, SO3, we saw the gas SO2 earlier, so that can come out of there. We saw the gas hydrogen sulfide earlier. So if we can pull those out, so here's the SO2 gas, then you can write the other products based on that. So this is an acid and sodium sulfite. So that's water and a salt. And then here we actually have a precipitation and a gas evolution reaction going on here. So that's the extent of gas evolution that we're talking about. Okay, so very few things that we have to say about that, but two aqueous react, form, and a gas comes out. The last one is oxidation reduction reaction. So this is the last topic here in this introduction to aqueous, but I really want to just give you a few highlights here because you take CHEM200 at Miramar and we spend a whole week and a half on redox reactions. So, you know, I've got, let's see, what is it, 6 slides, 8 slides, not a lot on this, but I do want to put a few highlights, okay? So this is electrons being transferred. The definitions is oxidation is a loss of electrons, or reduction is a gain of electrons. So Leo the lion goes grr. Yeah, I know it's bad, but this is lose electrons, that's oxidation. Gain electrons, that's reduction. Okay, so again, as we started this chapter, you got to have the terms to keep them clear. These are the kind of reactions that I want you to see for oxidation reduction, okay? So this is not easy though. Sodium is here an element. Elemental sodium has no charge. So I'm putting up here a 0 on no charge. Then we go over here and we form an ionic compound, and sodium has a positive 1 charge. Okay? Chlorine, elemental chlorine, there's no charge in the top right. That means it's 0. And over here we know that's an ionic compound. That's chloride, that's -1. So if we go from a 0 to a -1 and a 0 to a +1, this is where I want you to feel confident in what happened to the electrons. Okay, so remember electrons are negative, so sodium lost an electron and became a cation. Chlorine gained an electron and became chloride. So that goes to our definitions then. Sodium is oxidized and chlorine is reduced. So that's the terms. So what I did was show you the elements are 0 charge and then the ions are +1 and -1. Well, we have a lot other reactions than ionic compounds. So here, that's an element. This is an element, but this is a covalent compound. That's not an ionic compound. So when you work with redox reactions, they use a numbering system to help identify where do the electrons go. It's kind of like formal charge, how we used in Lewis structures. We said, is that atom, meeting its octet? Is that atom happy with what it has, with its valence electrons? It's kind of like that. So the rules would show you that hydrogen have a 0, oxygen have a 0 because those are elements, and the rule actually says hydrogen goes first and gets a +1 oxidation number. So these are oxidation numbers now, not charges, because remember that's not an ionic compound. So hydrogen is not +1, but its oxidation state, or its oxidation number, is +1. And if there's 2 of those, that's +2, and the compound is overall neutral, so that's a -2 for oxygen. I know you're used to oxides being -2, so that doesn't look new, but this is a new thing because it's saying these are giving positive, negative numbers to covalent compounds. So then, of course, we can go and say 0 to +1, oxidation, 0 to -1 or -2 is reduction. So this is what happens in oxidation reduction reactions. So I just want you to look at the simple examples. Elements, 2 compounds. The ionic compound we saw here, that's a little more straightforward because that goes to positive and negatives. And here, covalent compounds, but there's rules to give different numbers to them. So what I just talked about was oxidation state or oxidation number. So that's in parentheses. Okay, this is a fictitious number like formal charge. It just helps us. That's called oxidation number or state. And it's saying, what if have all the shared electrons assigned that one atom with the greatest attraction for those electrons? So the rules, I'll have them listed here, but again, the examples I showed you were elements going to an ionic compound and elements going to simple covalent compound. But you can see the rules, applying oxidation state rules. The one I just went through, because all of these are things that you know, +1, +2 for alkaline earth metals. So the oxidation state, you see the plus is written in front. Typically we write charges like this. So this is even indicating this is an oxidation state. It's different than a charge. So for the nonmetals, I showed you this example where I assigned hydrogen +1. I did that first because it has priority. This works down. And then oxygen -2. So what I mean by that is if we had hydrogen peroxide, for instance, we would assign hydrogen a +1, and that gets a total of +2. So in this case, oxygen's actually -1 because the charges on this one have to be canceled by the charges on this one. It has to equal 0 overall. So this is just an introductory to oxidation states and redox reactions. Like I said, what I want you to be familiar with is elements going to ionic compounds. That shows the oxidation states the easiest. And then I also gave the example of elements going to a compound. So I've left 4 slides here for you. If you're interested in more of this, you will see this in biology, biochemistry, and general chemistry 2, but that's where I will save this, is for general chemistry 2 for my classes. So please email me or come to office hours if you want to go over this material.